In this video, I will walk you through some multiple choice questions from past AP Calculus exams pertaining to area and volume. Number 1. The area of the region bounded by the curve y equals e to the 2x, the x-axis, the y-axis, and the line x equals 2 is which of these? Let's start by sketching the region. Y equals e to the 2x is an exponential growth curve. The x-axis and y-axis are part of the boundary, and the line x equals 2 is a vertical line at 2. So this is the area of which we speak. In general, if we integrate with respect to x, we can find the area between two curves between a and b if we integrate the top function minus the bottom function. In this case, the top function is e to the 2x, and the bottom function is 0, which we don't need to write. This region goes from 0 to 2, so these are the limits of integration. Let's integrate by doing some mental u substitution. Imagine that u is 2x. Then we know that u prime will be 2. Whenever u prime is a constant, we know that the only change once we do the u substitution is that we will end up dividing by u prime. So we know that on the next step we will have a 1/2 out in the front. Other than that, we can just go ahead and do the antiderivative. So the antiderivative of e to the u is e to the u. Let's apply the limits of integration from 0 to 2. So this means that we need to find the value at 2 minus the value at 0. When I have a constant, I like to leave the constant out front. Just personal choice. I could repeat this 1/2 minus 1/2, but I like to leave it out in the front. So this is the value at 2 minus the value at 0. But this is 1/2 times e to the 4th power minus 1. E to the 0 power is 1. And if I now distribute the 1/2, that gives me 1/2 e to the 4th power minus 1/2. This matches option C. Number 2, the region in the first quadrant bounded by the graph of y equals secant x, x equals pi over 4, and the axes is rotated about the x-axis. What is the volume of the solid generated? Before I draw the real sketch, I need to remind you what the graph of y equals secant x looks like. Remember that secant x is the reciprocal of cosine. So here is a dotted graph of the cosine function. The secant graph will have an asymptote anywhere cosine is equal to 0. So there will be a vertical asymptote at pi over 2 and 3 pi over 2. The graph of secant will touch the cosine graph at the max and min. So I will start at the max and approach the asymptote. And I'm going to start at the min and approach both asymptotes. At the max, approaching the asymptote. So this is what the secant graph looks like. However, we have a boundary at the vertical line x equals pi over 4. So this is the region we will rotate around the x-axis. If you rotate the region around the x-axis, you get a solid that looks like this. If you take a slice of the solid, it forms a disk, and we can use disks like this one to find the volume of the solid. It's a 3-step process. Step 1 is to find an expression for the radius of a disk. When the radius is vertical, we can find it by subtracting the top function minus the bottom function. In this case, the top function is secant x, and the bottom function is 0. And we don't need the minus 0. So our expression for the radius is simply secant x. Step 2 is to find an expression for the area of a disk. But the area of a disk is always pi r squared. Since we already have an expression for r, we can transform this into an expression for the area of a disk by writing pi r squared. Step 3 is to find an expression for the volume of the solid by integrating the area of a disk. Since we already have an expression for the area of a disk, all we have to do to form the volume is integrate. When you integrate the area of a disk, you are adding up all of the disks to form the volume. Since these disks are stacked horizontally, we will integrate with respect to x. And because the disks are stacked between 0 and pi over 4, these will be the limits of integration. Whenever there's a constant in the front, I like to pull it outside the integral before I find the antiderivative. The antiderivative of secant squared is tangent, because I know that the derivative of tangent is secant squared. So I'm going to leave the pi out in the front as I apply the limits of integration. So this means I need to find the value at pi over 4 minus the value at 0. So this will be pi times the tangent of pi over 4 minus the tangent of 0. The tangent of pi over 4 is 1, and the tangent of 0 is 0. So I'm left with just pi. So the answer is C. Number 3, the region enclosed by the graph of y equals x squared, the line x equals 2, and the x-axis is revolved about the y-axis. The volume of the solid generated is which of these? Y equals x squared is a parabola with vertex at the origin. The line x equals 2 is a vertical line at 2, and we also have the x-axis as a boundary. So this is the region we will be rotating around the y-axis. When you rotate the region around the y-axis, you get a solid that looks like a cylinder with a bowl carved out of the top. If you take a slice of the solid, it forms a washer, a disc with a hole in it. We can use washers like this one to calculate the volume of the solid. I'm noticing that the washers are stacked vertically. That means that ultimately we will have to integrate with respect to y. For that reason, we need to rewrite the equation of the parabola in terms of y. You can solve for x by taking the square root of both sides. So we get x is equal to the square root of y. Normally I would say plus or minus y, but we were told that this is in the first quadrant. Finding the volume of the solid is a three-step process. Step 1 is to find an expression for both radii of the washer. We will need an expression for the radius of the outer disk, which I will call big R, and we need an expression for the radius of the inner disk, which I will call small r. Let's start with big R. When the radius is horizontal, we can find an expression by subtracting the function on the right minus the function on the left. In this case, the function on the right is 2, and the function on the left is 0. So 2 minus 0 is just 2. Now let's find an expression for small r. The function on the right is the parabola, which is the square root of y. The function on the left is again 0. Radical y minus 0 is just radical y. So that's it for step 1. We have an expression for the big radius and the small radius of the washer. Step 2 is to find an expression for the area of the washer. You can visualize the area of a washer as the area of a big disk minus the area of a small disk. In other words, the area of a washer is pi big R squared minus pi small r squared. Since we already have an expression for big R and small r, we can write an expression for the area of a washer by writing pi big R squared minus pi small r squared. The last step is to write an expression for the volume of the solid by integrating the area of a washer. Since we already have an expression for the area of a washer right here, all we have to do to find the volume is integrate. Because the washers are stacked vertically, we will integrate with respect to y. But what will the limits of integration be? The washers are stacked vertically. I see that they are stacked starting at 0, so the lower limit of integration will be 0. But I don't know at this moment how high the region goes. To find the upper limit of the region, we need to find the intersection point between the parabola and the line x equals 2. So we can just substitute the x value of 2 into the equation y equals x squared. That means that y is equal to 2 squared, which equals 4. That tells us that 4 is the intersection point and 4 is the upper limit. So this is an expression for the volume of the solid. Before I evaluate the integral, I like to simplify as much as I can. Both terms have a pi in it, so I'm going to put the pi out in the front. Also, 2 squared is 4. And if you square a radical, the radical goes away. So we just have y. The antiderivative of 4 is 4y. The antiderivative of y, I increase the exponent by 1. I divide by the new exponent, so I have this. I still have that pi out in the front, and I'm going to apply the limits of integration. This tells me to find the value at 4 minus the value at 0. So I'm going to keep the pi out in the front as I find the value at 4 minus the value at 0. I can see that both terms have a y, so it's easy to see that the value at 0 will just be 0. So we have 16. 4 squared is 16. Half of 16 is 8. 16 minus 8 is 8, so we have 8 pi. This is the volume. So the answer is A. The last 3 problems are calculator active, so we will use our graphing calculator as needed. Number 4. If k is between 0 and pi over 2, and the area under the curve y equals cosine x from x equals k to x equals pi over 2 is 0.1, then k equals which of these? First of all, remember that the graph of one period of cosine x looks like this. So here's the part of cosine x that falls on the interval between 0 and pi over 2. So they're saying there's a k value somewhere on this interval where the area under the curve between k and pi over 2 is equal to 0.1. So this yellow area for some value of k is going to equal 0.1. Let's set up an expression involving k for the area of this region. So the area under the curve cosine x between k and pi over 2 would be given by the integral from k to pi over 2 of cosine x. So this is an expression for the area of this region, and we want to find the value of k where this area is equal to 0.1. So let's go ahead and do what we can to evaluate this integral. The antiderivative of cosine is sine, and we have the limits of integration from k to pi over 2. And all of this equals 0.1. This means that the value at pi over 2 minus the value at k should equal 0.1. In other words, the sine of pi over 2 minus the sine of k should equal 0.1. The sine of pi over 2 is 1. So we have 1 minus sine k is equal to 0.1. Subtracting 1 from both sides, we have negative sine k is equal to, dividing both sides by negative 1, we have sine of k is equal to 0.9. To solve for k, we need to do the inverse sine of 0.9. Let's put this in the calculator. Make sure your calculator is in radian mode. And we do the inverse sine of 0.9. 1.119, or if you round, 1.120. So the answer is D. Number 5. What is the area of the region in the first quadrant enclosed by the graphs of y equals cosine x, y equals x, and the y-axis? The line y equals x is a diagonal line like this. Cosine x starts at 1 and begins to fall from there. So this is the area that we need to find. If we integrate with respect to x, we can find this area by integrating the top function minus the bottom function. In this case, the top function is cosine x and the bottom function is x. But what are the limits of integration? From left to right, the region goes from 0 to something. So I know the lower limit is going to be 0. The upper limit will be the x-coordinate of this point of intersection. Let's use the graphing calculator to find the intersection between these two functions. Let's start by typing the two functions into the calculator. So let's hit y equals and type in both of the functions. Let's hit zoom 6 and take a look at what we have so far. It looks like all of the actions taking place in a small area right here. I'd like to zoom in on that a little bit. So I'm going to try zoom box, which is just a lot of fun. Move the pointer to the lower left-hand corner of where all of the action is. Oh, it's moving so fast. And hit enter. And then move to the upper right-hand corner and hit enter. We want to find this point of intersection. So hit second trace and choose option 5 for intersection. Move the pointer close to the point of intersection and hit enter. When it says second curve, hit enter again. When it says guess, hit enter a third time. So the intersection is 0.739. Before we even write that down, I would like to store this into a letter on my calculator. So hit second mode, quit your way out of here, immediately type the X button and the store button. I want to store this value into letter A. So I will hit alpha A and hit enter. So now all of these decimals have been stored into letter A. Now let's write this into our work. Let's write down that A is equal to 0.739, approximately. So somewhere in your work it needs to say that A is equal to 0.739. Of course there are more decimals to that, but those are being stored in the calculator. So we can actually go ahead and just put A right here as the upper limit of integration. As long as you have defined it in your work, it's all good. And now we can use our calculator to evaluate this integral, now that we know both limits of integration. So let's go back to the calculator. For integration, we will hit Math and choose option 9. We are integrating from 0 to a, so go ahead and put 0, and then put a. And we're integrating cosine x minus x. So cosine x, I'm going to close the parentheses there, minus x. And that's it. 0.400. So the answer is C. Number 6. The base of a solid is a region in the first quadrant bounded by the x-axis, the y-axis, and the line x plus 2y equals 8, as shown in the figure. If cross-sections of the solid perpendicular to the x-axis are semicircles, what is the volume of the solid? When they talk about a solid whose base is a particular region, I want you to picture an oddly shaped loaf of bread that is sitting on that region. In other words, picture a loaf of bread who has this kind of triangular footprint, and we're looking down on the bread from above. When they talk about cross-sections perpendicular to the x-axis, they are talking about slices like this one. Because the slices are stacked up from left to right, we know that ultimately we will have to integrate with respect to x. For that reason, we need to rewrite this function in terms of x. So let's take it and solve for y. So we have x plus 2y is equal to 8. Subtracting x from both sides, we have 2y is equal to 8 minus x. And dividing both sides by 2, we have y is equal to 4 minus 1/2 x. So this is what we will use as our expression for this line for this problem, 4 minus 1/2 x. We can use slices like this one to find the volume of the solid. It is a three-step process. Step 1 is to find an expression for the length of the base of a single slice, which I will call b, shown here as this yellow segment. When the slices are vertical, you can find an expression for the base by subtracting the top function minus the bottom function. In this case, the top function is 4 minus 1/2 x, and the bottom function is 0. But we don't need the minus 0 part. So that's it for step 1. We have our expression for base b. Step 2 is to find an expression for the area of a single slice. Remember, we are looking down on this solid from above. But if you pulled out a slice and looked at it, we are told that the slice would be in the shape of a semicircle. And we need to find an expression for the area of this semicircle in terms of b. There are a handful of shapes that are commonly used as slices on the AP exam. And I want you just to memorize the formulas for the areas of those slices in terms of base b. The first one you don't really have to memorize because it's just common sense. If the slice is a square with base b, then obviously the area will just be b squared. Rectangles, you just have to kind of figure it out using common sense. So I want you to focus on these last 4. Okay, I want you to memorize these 4. They're very common. If you have an isosceles right triangle that is set up this way, where the base of the triangle is one of the legs, then the formula for the area is 1/2 b squared. If you have an isosceles right triangle, a 45-45-90 triangle, where the base of the triangle is the hypotenuse, then the area is 1/4 b squared. This sort of makes sense compared to the first one I showed you. If a whole square, the area is b squared. If you set up your triangle this way, it's half of a square, so it should be 1/2 b squared. If you set up your triangle this way, it's a quarter of a square, so it's 1/4 b squared. So that might help you to memorize it. But what about the other two? Very often they will give you an equilateral triangle with base b. And here's the formula for that. Radical 3/4 b squared. And very often they will give you a slice in the shape of a semicircle with base b. And the formula for the area of that is pi/8 b squared. Notice that they all have b squared in it. So if you remember that, all you really have to memorize is the coefficient for each case. For this problem, we are told that the slices are semicircles, so we will use pi/8 b squared. Again, our goal is to write an expression for the area of a single slice. Since the area is pi/8 b squared for a semicircle, and we already have an expression for base b, we can turn this into an expression for area by writing pi/8 b squared. Now we have an expression for the area of a single slice. The last step is to find an expression for the volume of the solid by integrating the area. Since we already have an expression for the area of a single slice, we can find the volume by integrating. We notice that the slices are stacked up from left to right, so we will integrate with respect to x. And we notice that the slices are stacked up between 0 and 8. So these are the limits of integration. So all we have to do is put this into our calculator. So we will be integrating from 0 to 8. So hit Math and choose option 9 for integration and type in the limits of integration from 0 to 8. What's next? We have a pi/8. So let's do pi divided by 8. And then we're going to have to square something later, so we need some parentheses in here. 4 minus 1/2 x quantity squared. So 4 minus 1/2 x, and then close the parentheses and square it. I think that's it. Kabam! 16.755. So the answer is C. So that's the end of the problem, but here's a quick side lesson. I want to show you how I came up with this formula for the area of a semicircle with base b. We know that the area of a circle is pi r squared. So it makes sense that the area of a semicircle will be 1/2 pi r squared. But r is the radius of a circle. What is the radius of this semicircle that has base b? Well, the radius is just half of this base. So the radius will be 1/2 b. So I'm going to make that substitution. So the area of the semicircle becomes 1/2 pi, and instead of r, I'm going to put 1/2 b. We can simplify this by squaring 1/2 b. So I'm just going to bring down the 1/2 pi. 1/2 squared is 1/4. And then, of course, b squared. Simplifying further, we have 1/2 times 1/4, which is 1/8. So that leaves 1/8 pi b squared. And 1/8 pi is the same thing as pi/8. So we have area is pi/8 b squared. And that's how I got this formula. You do not want to have to derive this formula in the middle of a test. So again, I encourage you to pause the screen and memorize these 4 formulas. They all have b squared. So you just have to memorize which is the right coefficient for each situation.